Completed a degree in veterinary medicine at the Pontifical Catholic University of Minas Gerais in 2012, an MBA in agribusiness at the University of Sao Paulo in 2015, and a master's degree in animal science specializing in genetics and animal breeding in 2019 from the State University of Southwest Bahia. Thales is currently completing his PhD in genetics and animal breeding at Sao Paulo State University, where he is investigating a genome-wide association study focused on the identification of genomic regions and functional genes associated with disqualifying traits in the lower cattle under the supervision of Professor Roberto Carvalheiro. Since December 2021, he is a visiting scholar at Michigan State University under the supervision of Professor Cedric Gondro. And with that, Thales, I'll pass it over to you.
Okay. So, good afternoon, everyone. I would like to thank CGIL for the invitation and the opportunity to present part of my research I have been developing during my PhD. It's an honor for me to speak to such an important group. Here's an overview of this presentation. We will start with some considerations about this subject. Then we will go to genetic analysis of the traits evaluated in this work. And finally, we will see the GWAS and functional analysis of candidate genes annotated for these traits. Some data to contextualize Brazil's position in the world beef market. In 2020, Brazil became the country with the largest cattle herd in the world, with 217 million herds, representing 14.3% of the world's herd. Also, in 2020, the country found itself in the position of largest exporter beef in the world, with 14.4% of the international market, or 2.2 million tons. However, Brazil was only the third place in value, with $7 billion, being surpassed by Australia with 8.5 billion and USA with 8.1 billion. And the price obtained by the country in the foreign market is a reflection of the quality of the meat produced and the market that this product supplies, which are countries with lower quality requirements and which consequently pay a lower price for the product. Regarding to the quality of beef produced in Brazil, 2 points should be considered. The first one, the extensive production method, which consists of raising cattle in large areas of pasture with low investment and less control, which results in a lower quality of the final product. And second one, the herd predominantly of Zebu or Indian breeds, which are adapted to the adverse environmental conditions, such as hot and humid summers, dry winters, high incidence of internal and external parasites, low supply and quality of forages. I like this photo because I think it represents the adaptability of Nelore breed to the average Brazilian conditions. Here we have a lot of pregnant cows at noon due to the position of the sun in the middle of the dry season on north of the country. And the fact that most are lying down indicates that they are in a good condition of animal welfare despite environmental conditions. So to improve the quality of exported meat and reach more demanding markets, the Brazilian herd, predominantly Nelore, a breed that corresponds to 80% of the national herd, needs to be genetically improved. These two photos of the same Nelore cut show that there is genetic variability in this breed for meat quality traits, such as marbling. However, the country still cannot produce enough genetically superior bulls to meet its annual replacement demand. Even if all males from the breeding programs at weaning age were used, as well as bulls with special certificate of identification and production granted by the Brazilian Ministry of Agriculture, there would still be a deficit around 48% of replacement bulls. In programs authorized to issue SAPE, 20 to 30% of the best animals each year become candidates for certification. But an important part of these animals ends up not receiving the certificate for the identification of morphological and functional problems that determine the disqualification of the bulls. Thus, the deficit of breeding bulls in the country is further compounded by loss due to disqualifying traits. One of the main functional problems observed in beef cattle in safe programs is testicular hypoplasia, which is a genetic alteration characterized by the incomplete development of the germinal epithelium of the seminiferous tubes due to the inadequate number of germ cells in the testes. This leads to a decrease in sperm concentration and an increase in sperm morphological changes. A worrying fact is that most bulls with this problem are subfertile, that is, they have a reproduction success lower than the general average of the population, but they can still transmit this undesirable condition to their offspring. Another functional problem of high importance is the fetal legs malformation that can compromise the welfare and longevity of the affected animals. And given the extensive production conditions of most Brazilian herds, in which animals usually have to walk long distance in search of water and food, those with better conformation of legs and feet are favored. Reproductive performance is also affected, as good conformation of the legs and feet is essential, both for the male to be able to mount and for the female to be able to support the weight of the sire. In this second part, we aim to estimate the genetic parameters for testicular hypoplasia and fetal legs malformation, estimate the genetic correlations between testicular hypoplasia and scrotal perimeter, and between fetal legs malformation and yielding weight, because these two linear traits are already under selection in breeding programs participating of the Nelore Alliance. And finally, estimate the genetic trend for these traits in our Nelore cattle population. Phenotypic and genealogical data from more than 1 million animals from the Alliance Nelore database born between 2001 and 2017 were used. Contemporary groups were defined by concatenating the effects of year and season of birth, sex, only for the fetal legs malformation, farm at weaning and yearling, management group at weaning and yearling, and evaluation date at yearling. Contemporary groups data with less than 10 records and or without variability for these traits were excluded, and genetic connectability between contemporary groups was verified using the IMC software, and only contemporary groups with at least 10 genetic links to other contemporary groups were maintained. After this data consistent check, around 207,000 records were kept for testicular hypoplasia and around 295,000 for fetal legs malformation. So many polygenic traits, such as production and body measurements, show continuous variation. However, some disorders, such as testicular hypoplasia and fetal legs malformation, show discontinuous variation with affected or non-affected individuals without an intermediate state. And the threshold model allows this phenomenon to be explained. The liability is the term used to collectively describe all the factors that together contribute to the development of a multifactorial disorder. At the point where an individual accumulates a certain liability, he will be affected by the disorder. And the liability level at which this occurs, we call threshold. In the matrix model that was fitted in both traits, we have the vector of liabilities, the vector of fixed effects, including the contemporary groups and the age of which the animals were evaluated as linear and quadratic covariates, the vector of additive genetic effects, and the vector of residual effects. And it's important to say that since the residual variance is not estimated for binary models, the parameterization equaling to 1 was used. The variance components estimates were obtained by Bayesian inference using the THR-Gibbs software from the BloodPath19 family. In this analysis, with the objective of evaluating a possible correlated response resulting from the selection in the programs, data from scrotal circumference and with testicular hypoplasia and yielding weight with fetal legs malformation were used adjusting a threshold model in by trait analysis. The convergence of the chains was achieved using Markov chains of 500,000 cycles in both analyses. Initial discard of periods of 6,000 cycles for testicular hypoplasia with scrotal circumference and 50,000 cycles for fetal leg malformation with yearly weight, and sampling intervals of 68 cycles for testicular hypoplasia with scrotal circumference and 50 cycles for fetal leg malformation with yearly weights. As a result, this graph shows the evaluation of the incidence of these disqualifying traits in the population, considering all available records in the database before the data consistency checks. Then an increase in the incidence in both traits is observed, reaching values close to 3% in recent years. However, this increase should be observed with caution because it may reflect the lack of standardization of assessments over the years, especially in fetal leg malformation. Where the assessment method is more subjective. As the technician becomes more capable, he becomes more discerning. This other graph shows that in this population, males tend to be more affected than females by fetal leg malformation. And this difference may be related to hormonal difference between sexes affecting the growth curves of males and females, and consequently weight gain. Some studies show that in the Nelore breed, the growth of males differs little from that of females in the pre-weaning phase, but with increasing age, this inequality intensifies. In this table, we have a summary of the data used to estimate the variance components and heritability of the data clean described before. And with cleaner data, the incidence values stand out, approaching 5% in both traits. These values are equal to other than those already reported in the literature in studies with smaller numbers of animals, which suggests that the percentage incidence in the population remains constant or increases even with a larger database. As expected, linear traits showed height values for heritability. On the other hand, the binary traits had heritability estimates of medium magnitude. Unit trait analysis were also performed for the binary traits for comparison purpose, and the heritability estimates obtained were very similar, 0.15 for hypoplasia and 0.17 for malformation. And these values indicate us the existence of variability in these traits, and that this variability would be influenced to some extent by additive genetic effects. Other works used as reference reported similar heritability for these traits. The genetic correlation between testicular hypoplasia and scrotal circumference was close to 0. And to compare, it was suggested to estimate the correlation between the genetic values of the bulls obtained in unit trait analysis for testicular hypoplasia and scrotal circumference. And the value found was 0.02, corroborating the lack of correlation between these traits. Yearling weight and fetal leg malformation show a negative genetic correlation, but of low magnitude. And the conclusion from this result and from other studies that use it as different approach is that animals with walking difficulties due to the congenital malformation tend to gain less weight. The genetic strengths were also estimated by linear regression of the posterior means of the predicted genetic values for each trait over the year of birth of the animals. And the trend shows that the strategy of discarding animals with problems has contributed to the genetic progress of these traits in the population. And a question that came up from Professor Cedric, my advisor here in the USA, was why the incidence increasing if the genetic trend points are decreasing. So a possible explanation would be the increase in the rigor of the assessment by the technicians combined with a greater systematization of the notifications in recent years. As conclusions, the estimates of additive genetic variability and heritability obtained for testicular hypoplasia and fetal leg malformation agree with previously reported values and suggest that the incidence of these problems in LR cattle can be reduced through selection. The traits scrotal circumference and yielding weight show a null and low magnitude genetic correlation with testicular hypoplasia and fetal leg malformation, and this could have implications for the selection criteria used by breeding programs. And finally, the trend of increasing incidence shows the importance of intensifying the selection against these disqualifying traits, despite the favorable genetic gain observed in the genetic trend curve during the evaluated period. So in this third part, we performed the GWAS to find windows of adjacent SNP that are significantly associated with testicular hypoplasia and fetal leg malformation in LR cattle using the weighted single-step development methodology, as well as identifying the main candidate positional genes with functional evidence and the potential role in the incidence of these two traits in the studied population. Data from around 6.6 thousand animals genotyped with high-density panel with approximately 800K markers were used as reference for the genotype imputation of around 28,000 animals genotyped with medium density panels. And the imputation was performed using the FImpute software. Then a quality control of the genotypic and pedigree data was performed by using the KCF19 software from the BluePath19 family, following these values on table 7 as exclusion criteria. In the GWAS, we use the same pedigree and phenotypes that data of the part 2 and the genotypes of 17,000 animals for hypoplasia and 12,000 animals for malformation with 461,000 SNPs each. The BluePath19 family software was used, and the method to estimate the animals' estimated breed values was the weighted single-step GBLUP, and the solutions of the SNPs were obtained by backsolving. The windows of 20 adjacent SNP that explain more than 1% of the genetic variance of the trait were selected for annotation candidate genes. A trained list of genes associated with relevant keywords for each trait was created using GeoDefy web server, and this list was used in top gene suite along with a list of candidate genes located within the Windows test list. Then those candidate genes with a functional profile significantly similar to the profile of the genes on the trained list were selected. The presence of genes in Windows of up to 100 kilobases upstream and downstream of the main windows was also evaluated, as their effect can be captured by neighboring SNPs due to linkage disequilibrium. In addition, windows were also examined manually or visually in Assemble Genome Browser, just in case automated gene annotation failed to detect the associated gene near the coordinates, which is what happened. So for testicular hypoplasia, 12 windows explain more than 1% of the genetic variance, and the sum of the variance explained by those windows correspond to 18.404% of the total genetic variance for this trait. The window that explained the highest proportion of variance, 2.28%, was located in BTA14, and 86 SNPs were found in this region, although no candidate genes was prioritized in this window. However, by visual inspection in this genome browser, it was identified that the KHDRBS3 gene is relatively close to this window, 219 kilobases from the final position, and appears to be in linkage disequilibrium with it. The star gene located on chromosome 27 was the only gene with significant p-value in the prioritization analysis automated by TopGene. Erlin2 also on chromosome 27 and GPX5 on chromosome 1 were not significant according to the top gene analysis, but both are expressed in the epididymis of the male reproductive tract of mammals. Talking now a little about the functional notation of these genes, the protein transcribed by the key HDRBS3 gene was found in the nuclei of certain cells and germ cells at different stages of spermatogenesis. In addition, a similar protein, SAM68, is reduced in the tests of men with azoospermia. In this work, Gross et al. 2020 found that epigenetic marks associated with these genes are differently present between bulls with high and low fertility. The STAR gene is one of the most important factors associated with testosterone production in Leydig cells. Risotto et al. 2020 and Aspen et al. 1998 observed alterations in the expression of these genes in bulls under the effect of heat stress and administration of exogenous hormones. And Pilon et al. 1997 observed the expression of these genes even in fetal bovine testes. The ERLIN2 gene on BTA27 is involved in the regulation of the cellular cholesterol homeostasis, and according to Kim et al. 2018, the protein encoded by these genes was expressed in epididymal sperm, suggesting the potential involvement in maintaining the integrity of the spermatic neck. The GPX5 gene on BTA1, also present in the bovine epididymis, encodes a protein involved in protecting the sperm membrane from the harmful effects of lipid peroxidation during the oxidative stress. And Frekakovic et al. 2017 estimated inbreeding depression and reproductive aspects of simmental bulls and found markers on chromosome 1 associated with semen quality trait close to the GPX5 gene. Some results for feet and legs malformation. 12 windows also explain more than 1% of the genetic variance for fetal leg malformation, and together these windows explain 16.37% of the total genetic variance. I'm sorry. Four genes were prioritized by top gene analysis and are associated with skeletal muscle development, aberrant bone growth, lipid metabolism, and intramuscular fat deposition, which suggests the involvement of these genes in expression of fetal legs malformation in the studied population. By visual inspecting of the windows, two more genes were identified that showed a relationship with this trait. These genes play important roles in the biology of bone cells and in determining the length of line bonds. The ATG7 gene is linked to the flow of autophagy, which is important for preserving the muscle mass. In mice, the deletion of these genes in muscle resulted in profound muscle atrophy and age-dependent muscle decrease in strength. Nakanishi et al. 2019 correlated the increase in gene expression of ATG7 gene with skeletal muscle growth and body weight in beef cattle by verifying that during the fattening period, the expression of this gene increased regardless of the muscle evaluated. The XT1 gene on BTA14 is involved in metabolic pathways related to fibroblast growth factor type 2. The interaction between growth factors and the receptor is regulated by the amount of heparan sulfate. And according to Duncan et al. 2001, somatic mutations in XT1 would cause a defect in heparan sulfate biosynthesis and a disruption in the negative feedback loop that regulates the chondros proliferation and mutation, allowing premature differentiation and therefore aberrant bone growth. The ETJ1 and PPARD genes are related to lipid metabolism. In Korean Hanu cattle, Lee et al. 2013 associated the ETJ1 gene with intramuscular fat deposition, and Harold Saldana et al. 2020 identified also in the Hanu breed that the TJIA1 gene plays an important role in the development of marbling. And the PPARD gene plays a role in promoting the use of long-chain fat acids, a substrate for oxidation in cell membranes during the differentiation in rumen development. And its expression was increasing in newborn Holstein calves in response to a better nutritional plan. This suggests a relationship with accelerated growth and rapid weight gain. Regarding the genes identified by visual inspection or of significant windows for fetal leg malformation, the defective SCUB trace gene function is associated with problems such as craniofacial and dental defects, reduced body size, and defective endochondral bone growth in mice, as well as osteosarcomas in humans. And the SHOX gene also seems to have a relevant role in skeletogenesis, being associated with short stature and limb deformities in humans, such as in Lady-Way dyschondrosteosis. And Rafati et al. 2016 found a complete association between the presence of SHOX gene deletions and skeletal atavism in Shetland ponies. That is an inherited disorder characterized by abnormal growth of the ulna and fibula, causing abnormal skeletal muscle and impairment movement. As conclusions, the present GWAS allowed the identification of chromosomal regions associated with testicular hypoplasia and fetal leg malformations in LR cattle, and provided possible evidence on the genetic architecture and biological process related to the development of these traits. Positional candidate genes with functional evidence and potential role in the incidence of the traits in the study population may not be prioritized by the top gene analysis simply because of the bias in databases. So visual inspection of meaningful windows in the genome browser remains important. And finally, more research is needed, and future investigation into the candidate genes prioritized here can serve as basis for accurate mapping studies with the aim of identifying causal mutation that may contribute to the understanding of the genetic and morphological mechanisms that regulate these traits. In the fourth chapter, which will compose the final version of my thesis, we are using sequence bull sample around 26 million SNP after quality control to redo the GWAS and then compare the results. I would like to thank CGIL for the opportunity, and also remember and thank those who have guided me and helped me in this work. Professor Roberto Cavalheiro, my advisor, Cedric Gondro, my international advisor at MSU, and Lucio Albuquerque, my co-advisor at UNESP, Haroldo Neves from Gensis, Pablo Fonseca, postdoc at University of León in Spain, Delvan Silva, now a professor at Federal University of Viçosa, Giovanna Vargas, now on Zoetis, and Gabriel Campos, postdoc at UNESP. And also the PhD students, Ivan Carvalho Filho and Caio Teixeira from UNESP. And finally, I would like to thank the institution CAPES and CNPq for the final support, Gensis for providing the data, and MSU for having me and for the resources made available during this time here in the United States. And that's it. Thank you, guys.
Thank you, Thales. I'd now like to open it to the floor for any questions. So if you have a question, please raise your hand, and then you're more than welcome to turn your camera and your mic on. Not seeing any as of now, but I might just kick it off. Thales, for your parameter estimation, I seen that you just ran the threshold model. Is that correct?
Yes.
Did you investigate or compare using a linear model? And if so, were the results similar or was there much of a difference?
No, I didn't use linear models because the traits are, we have the phenotypes are binary phenotypes like 0, 1 for these animals, affected, not affected. So we just use the threshold model.
Okay. Any other questions for Thales?
Just in case you didn't see, there's a question from Tachi in the chat, Colin.
Oh, my bad. Tachi says, thank you for the presentation. I was wondering if you have presented the observed or liability heritability.
Sorry?
Tachi says
Could you
she was
repeat?
wondering if you presented the observed or liability heritability. So I think she was wondering if you converted from the liability scale to the observed scale.
No, it's the phenotypes is observed.
Flavio, do you have a question there?
Yes. Okay. Thales, thanks for the presentation. I have. I just like to clarify this what Tati asked before I ask a question. So now she was asking because you use a threshold model, right? And so you calculated the genetic parameters in the liability scale. So the question is, you use those parameters to calculate the heritability, and you present heritability on the line scale, or you converted the heritability to the observed scale?
Sorry, I didn't understand your question, Flavio. The audio is not so good.
Oh, okay. Yeah. So have when you calculate the heritability for the threshold trait, right?
Mm-hmm.
You converted the heritability to the observed scale or not?
No.
No. Okay. So it's in the liability scale.
Yeah.
Okay. I have a question for you. When you in this chapter for the various components, you said that Gibbs sampling was used to achieve convergence for the binary traits, for the two trait analysis, right?
Yeah.
So would this mean that when you tried with use just maximum likelihood, you didn't have convergence? Or was it just the way that you said?
No, I didn't try the maximum likelihood, just the Gibbs sampling.
Oh, okay. So it was just the way that you said.
Yeah.
It looked like that you tried with the maximum likelihood, didn't work, then you use Gibbs sampling.
Oh, yeah, sorry, no.
Yeah, no, I was asking because that's something that I always tell the students, right? If there is no convergence with the maximum likelihood, you should not use Gibbs sampling, because with Gibbs sampling, I was going to get a result, right? Because you have outliers there that stabilize, and you're going to get some posterior distribution, right? But in fact, you still have the same problem. It's just you mask the problem.
Yeah.
So that's what I like to clarify. Another thing is, which link function did you use? Was probit or logit?
Sorry?
Which link function did you use for the your analysis? The liability for the threshold analysis.
No.
Which link function was probit or logit?
Link function?
Yeah. Yeah, for the, you need for the to use a threshold model, you need to have a link function that convert your observation to the liability scale.
Hmm. Sorry, I don't remember this parameter on the program that I used.
Probably use the default one. Yeah. No,
Yeah.
that's fine. I was just curious to know what was the link function.
Flavio, considering that Thales, you used the Tresh Gibbs 1F90, didn't you?
Yes.
That assumes probit. It's the same as my analysis, yeah.
Yeah, so it's the default. There's
Yeah.
no change. Yeah, so then if it's probit, Thales, if you like, you can present your readabilities also in the observer scale. It will be easier to compare with probably most of the estimates that you're going to see in the literature. It's very simple to convert.
Okay.
That's why I was
Thales,
asking what was the link function, because if you use probit, then you can convert back.
Thales, I actually have that formula, so I can send it to you after.
Okay, would be good.
Thanks, Flavio. There's another question in the chat from Tiago, who missed the start due to connection issues, but he would like to know if you can show again how feet and leg traits were evaluated in the field and who did this work.
Hold on. How this work? So this trait is evaluated by technicians from the breeding programs, and they have it's more visually, and previous studies like there is a study from Giovanna Vargas that she studied two traits. One just look this fetal leg malformation as a binary trait, and another one like a trait with five different steps. And in this case, in my database, I just use this binary trait information, and the evaluations is done by the technicians at the field. They just look at the animals, and if the animal has any kind of malformation and problems in walking, they put qualify that animal as animal affected.
Perfect. Thanks, Thales. Any other questions?
I have another one, if it's possible. Nobody.
Yeah, sure, Flavio. Work away.
Yeah. Now, what I like to ask is this: the third chapter, I think, of your thesis, that is the GWAS.
Yes.
Have you submitted to publication? Yeah.
We are trying now.
Okay. Yeah. Now, I am also curious about the following. You use 1% of the variance, right? If the window is plain 1% of the variance or
1%,
more,
yeah.
then you look further, right? For
Yes,
the downstream
yes.
analysis. Have you asked to the software to calculate the approximated probability? Over here, you are working with windows. What you could do for the SNPs that are in within this window, because what we had as experience recently is that a lot of reviewers they are asking you once you submit the paper to go back and look at the probabilities or to do basically the test, right, of the marker effects to select the regions, right? Because what the argument is the variance, the way that we calculate the variance, explained by the windows depend on the allele frequency of the markers. And if the allele frequency is low, it's going to explain low variation, right? But the effect could be strong. It sounds not good. The way to go is to use the probability. But the problem is there's a lot of, we see a lot of results that the approximate probabilities don't follow the expectation. So there is a problem with the approximation. So when you look at the QQ plots, they are completely off. Right? And so I was just asking if you had experience with this, because maybe I'm going to face this problem, right? Yeah. I really like the variance, and if you like to prevent the effect of the frequency of the alleles on your decision, then you calculate the percentage of variance based on if the two alleles, let's say, have the same frequency at 50% to everybody, then you eliminate this. Right? You don't use the observed frequency, but you say no, everybody has 50%, and you calculate. So then it is going to reflect more the effect itself than the frequency, right? So then I think you can go around to this feedback, negative feedback from the reviewers, because they are right? If you have a low frequencies, you cannot explain a lot of variation, right? Yeah. Even if the effect is important. But if you, when you calculate there, you say no, it is 50%, then you eliminate this, and it's still, then you use the regions that explain more. And you're not going to have the problem that we are seeing with the probability, right? Because not in all cases the probabilities are well approximated. Especially in my observation and I did some thinking about this, how they are approximating, and I think the problem is we have many variants that have a low allele frequency, and that's affecting the approximation because you assume a normal distribution instead of t-distribution, and with when the alleles have a rare alleles or low frequency, that approximation is not good in a normal distribution. Yeah. So just heads up for you, if you didn't submit that, this type of discussion you might need to have.
Yeah, that's one of my main concerns about this methodology, because we have a problem in the methodology because the program uses the BLUP-F19. They don't give us the p-values when we are using the p-values for the SNPs when we are using the THR-Gibbs, like for binary traits. So we had to use the variance, the sum of the variance explained by windows of 20 adjacent SNPs as a result, because we don't have the p-values.
Yeah, I forgot that you use the Gibbs sampling. Yeah. So, but in this case, at least you should consider to do what I comment to you as one alternative is to use 50% to all alleles. Right, then you are going to reflect more the effect of the allele substitution effect than affect the allele than the frequency, right? Okay. Then you'll be not dependent on the frequency, because that comment probably will come from the review process. Yeah, the percentage depends on the allele frequency. If you have a low frequency, you're going to miss the region, right?
Yeah, I see.
Anyway, just for you to think about.
Okay, good. Thank you, Flavio.
Yeah.
Thanks, Flavio. I'll see you again. Any last questions? Anyone? I'm not seeing any. So I'd just like to thank you again, Thales, for the great presentation. And we'll see everyone again here next week. Thanks.
Thank you, guys. Have a great afternoon.
Thank you, Thales.
Thank you. Bye-bye.